Welcome to the explanation for the Unit 3 practice exam for AP Physics. I'm going to start with the multiple choice and then we're going to go on to the free response. So as a reminder, you should do the practice exam first as far as you are able and then watch this video. So any questions that you get wrong or you are confused about, those are obviously the ones you need to skip to. There are a few problems though that I definitely want to emphasize, all right? And so it might be actually instructive to watch the whole video even if you feel like you got most of the various parts. All right, so to begin, we have question number 1. Frequently people are concerned about this one because they will get answers like B is a popular one, all right? A lot of the time they'll treat it like this is a linear spring. And the main confusion is, all right, between linear versus nonlinear, and also, is this an equilibrium question or is this an energy question? Because they will ask both of those, and you have to be able to tell which one is which. All right, so before we actually answer the question, let's start with, how do you know whether they're asking you to use forces, and therefore it's an equilibrium question, or energy? All right, so if it's a forces question, then there will be some mention of something like, what is the equilibrium position? Or, you know, where will it hang when it, you know, comes to rest, or something like that. All right, and so that would be an equilibrium question. All right, so if we were trying to work this one out with equilibrium, we said, all right, where is the equilibrium position? All right, well, you know, maybe it stretches down, I don't know, this far. And when it's at equilibrium at that position, it's at equilibrium because the two forces that act on it, which would be the weight and the spring force, which happens to be alpha x squared, not the regular kx that we're used to, are equal. All right, so at this position, those two forces are equal because that's what equilibrium means. And so then that would give that the equilibrium position is the square root of mg over alpha. All right, now if you already went ahead and you looked at the answer key, that's not the answer. It's actually A, which is root 3 mg over alpha. Okay, so clearly then, they're not asking an equilibrium question. So what in the text is going to clue me into that? Well, it's talking about, you know, taking this thing and putting it at, you know, x equals 0 and then releasing it from rest. All right, so if we were acting this out live, what you would see would be, you know, it would be going boing, boing, you know, up and down like that. It would be oscillating back and forth between where it was released from and not the equilibrium position, right? It would be oscillating between the top and the lowest position. So this question is not asking where is equilibrium, but what is the maximum downwards displacement of the block? All right, well, questions of maximum and minimum for springs are going to be more related to energy than they are to forces, right? The maximum position down here would be where all of this gravitational potential energy has turned into elastic potential energy down low here. All right, so therefore at the lowest position, my picture would look like this, and I wouldn't be referencing forces at all. It would be a question of energy. All right, so gravitational potential energy becomes elastic potential energy. All right, so if it were just a regular spring, then I'd be doing mg, oh golly, what do I do for h? Well, since we started at x equals 0, the change in height is the extension of the spring. So mgx equals, all right, now, I started to say, if it were a regular linear spring, then we would say 1/2 kx squared. All right, unfortunately, it is not a regular linear spring. So 1/2 kx squared will actually get you the wrong answer. We've got to do something with this alpha x squared thing in order to get a potential energy formula. All right, so if you think back a little bit, the integral of force is work. All right, and then they're being a little bit sloppy with signs here. Technically, this force is negative alpha x squared, where the meaning of the negative sign is that if the extension is this way, then the force is in the opposite direction. All right, so they're being a little sloppy with signs here. Basically, we can just say, in this case, that if I take the integral of the force function, I will have the energy that is now stored in the spring. All right? All right, so if it's alpha x squared, the integral of a power function involves me adding 1 to the exponent and dividing by the new exponent. So that means that the potential energy formula is going to be 1/3 alpha x squared. Alpha x cubed. And so that's how they end up with the answer that they do. One of these x's cancels. So now that's x squared. Okay, multiply and divide, and we're going to get that x is 3mg over alpha square root of that. All right, there we go. All right, so that one, it took a long while to explain it, but basically you could have done the whole thing in about 30 seconds as long as you recognize that it was an energy problem, not a forces problem, and that you knew that because it was a non-linear spring, you were going to have to use integration to get the correct potential energy formula. They do like to use nonlinear springs on the AP Physics C exam. They also like to use linear springs, so you have to pay attention to which one it is so that you can integrate as needed. All right, number 2. We have done questions like this before, so I don't imagine this one's going to be too wonky for you, but the idea here is in order for it to make it around, there's got to be some initial velocity to this thing. And it has to be enough of an initial velocity. And making it around is determined by the forces that are acting on it at the top. So what are those forces? All right, well, gravity, all right? If it were going faster than it needed to go, there would also be a normal force downwards. However, in this case, the normal force is going to be 0 because they're talking about the minimum speed required. Right? So if this is going the minimum speed it has to, then when it gets to the top, it will be going slower, and the minimum speed required to make it around the loop-de-loop, which means it's just barely going to be brushing at the top of the track. And then centrifugal force. All right. So since there is no normal force at the top, that means these two are equal at the top. And then that means that the minimum speed at the top is root GR. But Mr. Errico, root GR is not the answer. That is correct. Root GR is not the answer. That is the speed at the top. They want to know what must the speed at the bottom be in order for that to be the speed at the top. So you have to start with forces to figure out how fast must it be going up here in order to figure out how fast it must have been going down at the bottom to still have that much speed when it got to the top. All right, so that now is going to be a conservation of energy question. Down here it's got kinetic energy. Up here it's got also kinetic energy. I'll have to call it K final. And it's higher up, so it's got gravitational potential energy. All right, so the K initial that it had down there equals K final plus UG. And if you plug in this for your final speed into your kinetic energy formula, and you plug in 2r for your height, because it's the diameter of the circle higher, then you can work it out to get that the initial kinetic energy would have to be root 5gr, is I believe what the answer worked out to be. All right, let's carry on to number 3, which is an important question, okay, but also I'm going to talk some extra stuff on this one, which is extra important because they won't always give you one like this where the areas conveniently cancel out. That's actually the key to this question, though, is it says, you know, all right, you know, which statement below is correct, and you got, you know, you read them through, and ultimately, you know, if it was initially moving at the beginning, right, since this area is the opposite of that area, the two areas will cancel out. So at the end of 20 seconds, it's going faster than it was at the start, but at the end of 40 seconds, it's back to the initial speed that it was already moving at. So therefore, the correct answer is C. The speeds at 0 seconds and 40 seconds are equal. All right, now, the broader point here, though, is that the integral of force with respect to time is the impulse. So they don't have to give you something nice and neat like this. They could give you something a little more messy where there's a collision and then a force versus time graph. All right, so let's say that it's like this. You've got a 2 kilogram block, 5 meters per second, hits a 6 kilogram block, and this is what the force versus time graph looks like because one of these has like a force sensor or something attached to it. All right, well, the area under this is going to be the impulse, and the impulse that each of the objects receives is equal and opposite. Equal and opposite for the two blocks. All right, so based on the scale I've got here, this top number says 600 newtons is the peak force, which is not actually outrageous for a collision. And then we've got, all right, 100, careful now, milliseconds for this 5th tick mark here. So that I guess means every tick mark is 20 milliseconds. So that means the time interval of the collision is 40 milliseconds, 40 to 80, based on my visual estimation here. All right, so if I do 1/2 base times height, we're going to end up with an impulse of, for this one, negative 12 Newton seconds, and for this one, 12 Newton seconds. Okay, because during a collision, the two objects involved receive equal and opposite impulses. All right, now what am I supposed to do with that? All right, well, for the first block, its impulse that it receives is going to be, let's see, the change in its momentum. So mv final minus mv initial. All right, its initial velocity was, let's say, in the positive direction. All right, so that means we're going to have 2 times 5 is negative 10. The impulse, however, was negative 12. All right, so a little bit of simple algebra here, and we're going to come up with the final velocity of the 2 kilogram block. That's got to be negative 1 meters per second. Okay, so it hit the 1, and now it bounced off, and it's going at 1 meter per second in the opposite direction. For the 6 kilogram block, it was initially motionless and receives an impulse of 12. Oh, and it's 6 kilograms. All right, so that means that its final velocity is positive 2 meters per second. All right, so they can ask more involved questions where a graph of force versus time is given. and know that the force versus time graph for a collision represents the impulse that each block receives. All right, part 2.